Morning, everybody. Hope you're having a good start to your week on this Monday morning. I saw that we had some ducks waiting early for the stream. I can't remember your personal Gmail accounts, though, your personal YouTube accounts. So, like Beetle. I think that was Riley. Darth Alias, don't remember Darth Alias. Maybe you're an Ursa Major. Anyway, I was also checking out the weather because we just had our first big nor'easter of the year. Well, not really the first. We've had others, but this was a bigger one. You can see that there's a low pressure up in southeastern Canada now, and there's a high pressure down the Atlantic. So all last week we're talking about how high pressure moves to low pressure, right? Well, why isn't the air here moving directly there in a straight line? Well, it's a simple reason. The Earth rotates. Earth rotates from the west to the east. So it's going to deflect air that direction. Talk more about that as we move ahead. But also down to the south, you have another little low pressure right here. These storms could maybe develop, but nothing too big like we've had recently. Until you get to, oh, I'm on the 16th, so I'm off. Where was I? Nothing too big, maybe until, a little later. Now I'll stay to the south. Maybe give us some snow tomorrow, some snow showers. Anyway, today on the agenda, obviously, any questions you have about anything to do with science or any assignments, we'll take a look at. We'll take a look at last week's IXL I posted on Monday about human impact on groundwater. No other questions. I will kind of introduce you to and read through an article I found earlier in the month, about a month ago in November, but didn't really apply to what we were talking about just yet. So I kind of hung on to this article so that we could talk about another time. From the University of Texas, their engineers have developed self-watering soil. Seems like it cuts out a middleman, literally. Could you have soil that waters itself? It's an interesting idea. Reminder to take a look in Aspen for your DNA number 9. Make sure that you are satisfied with your sheet and check score, and revise if you're necessary. And then obviously there's an IXL here for later on, identifying independent versus dependent variables. There was a typo in the agenda if you checked earlier this morning. It was a copy paste from the previous Monday about groundwater impacts. But focus on independent versus dependent variables, because I feel like that's something we got to work on going forward into the future. So we'll take a look at human impact IXL on groundwater, and then we'll talk about self-watering soil if you guys got nothing else. No other questions, comments, concerns? Gotta get 5 out of 6 right. I hope I do it. So last week, again, looking at the water cycle and looking at some data behind the water cycle, how humans are impacts on the water cycle. So this kind of introduction and then answering the questions on groundwater. Freshwater is a natural resource that humans use every day. Freshwater has many uses, including drinking, cleaning, taking care of livestock, irrigating farms, and generating electricity. Since 1950, the United States Geological Survey, USGS, basically the NASA of the Earth, has tracked the volume of freshwater used in the United States. The graph below shows the volume of freshwater withdrawn or taken by humans for any use in any given year. The data were collected every 5 years, starting in 1950 and ending in 2005. So it would be nice if they had an update here, because since it's 15 years old, really. Now, key word there is withdrawn, because it's going to be different from a word later on, and that's deplete. So withdrawn versus depletion. Okay? Withdrawing always meaning taking water out. So from 1950 to 2005, we clearly see a positive slope here until it levels off and is more zero after 1980. And then A line graph would probably be better. You don't really need a bar graph, but I understand the idea of a bar graph because you're showing how much water is withdrawn within those 5 years. And they're talking cubic kilometers, so not cubic centimeters. We're talking massive, massive amounts of water. So which one is supported by data? Volume of fresh water withdrawn per year increased steadily until 1980, or the volume of fresh water withdrawn per year increased every 5 years. So the second one suggests that there is a continual positive increase, and I should be ending up here somewhere. Is that true? No, it's not. Did it increase until 1980 and stay steady after that? It did. So it's kind of like a slope with a plateau on the top. So I'm going to pick that first answer. Humans withdraw a large volume of water from Earth. Only a small portion is used by people at home. Most of it is going to be used, especially in agriculture. People get fresh water from different sources. Two of the most common sources of fresh water are surface water and groundwater. We know that. Surface water is found on the surface of the Earth, hence its name. Groundwater is located underground, hence its name. But groundwater is also stored in what we didn't really talk about, but the official word for that, aquifer. So water underground sits in an aquifer. Right? To withdraw groundwater from aquifers, people must pump it out of the ground through wells. Despite this challenge, groundwater is a more reliable source of water than surface water in some regions. So it is more reliable in certain places because it is in a place where it can't really evaporate. So if you're not receiving rain over a long period of time, or you're exposed to lots of sunlight and high temperatures, you're not going to be exposed to excess thermal energy. You're not going to evaporate and become water vapor. So it can be a little more stable or reliable. I prefer the word stable, not always reliable. Especially during a drought. Groundwater is often still available. Well, it depends. Depends on how deep that well is and how big the aquifer is. I know up here in Rhode Island, that's not really the case this year. It wasn't exactly reliable. In which statement correctly explains why people use groundwater as a source of fresh water? Some environments, groundwater is the most reliable source of fresh water. Groundwater is located below the surface of the earth, so the water is easy to withdraw. Water is not easy to withdraw when it's underground. You have to build a well. So I'm going to go with something being a little more stable. It lasts longer if it's not pumped. Okay. The graph below shows the volume of groundwater and all the fresh water withdrawn between 1950 and 2005. So this is the total amount of fresh water used. In green is groundwater. So it kind of mirrors what we have for the total amount of water. Since 1950, looking at just the green, what percent of the fresh water withdrawn in the U.S. was groundwater? Is it over half? Is the green making up over half of a bar? Or is it about 1/5? I mean, you have close to 500 cubic kilometers here, and it's about 100 for underground. 100, 500, 100 divided by 5, about 1/5. United States, the volume of freshwater withdrawn has changed over time. To understand one possible reason why the volume has changed, look at how the population has changed. So they're showing you positive increase of population. Population's increased from 1950 to 2005 in the United States. Okay, we've basically doubled in about 55 years, which is impressive. Now, look at water usage. All right. Water usage is still that positive slope with a steady leveling off in 1980. 1980, population is still going up. So they want you to take a look at population size in the United States versus volume of water used. It's like the statement that's supported by the data. Between 1950 and 1980, the U.S. population and the volume of fresh water withdrawn increased, but the volume of fresh water withdrawn increased by a smaller factor than the population did. So they're suggesting here that they both increased, but fresh water withdrawn, the amount of water used, increased by a smaller amount than population. So they're saying that they're both a positive slope, but population had a continual, almost a linear increase. This one is kind of flattening out the top. Between 1950 and 1980, the volume of freshwater withdrawn approximately doubled. The volume of freshwater supported the population also increased. So they're saying that the water doubled. True. 200, maybe 250 to 500. It doubled. But they're saying that it continued to increase to support the larger population. Did it continue to increase? No. Don't know about that one. Alright, what's your explanation here? This means the volume of freshwater withdrawn increased by a larger factor than the population. So this statement is not supported by the data. This means that the volume of freshwater withdrawn increased by a larger factor. The volume of freshwater withdrawn increased by a smaller factor. How are you saying... Okay, whatever. How are you saying something completely different? Opposite. Look at the same graphs. Think about how the population and the volume of freshwater withdrawn changed between 1980 and 2005. Between 1980 and 2005, the population increased steadily, but the total volume of freshwater withdrawn changed only slightly. Okay. Between 1980 and 2005, the population increased steadily, so more freshwater was needed to withdrawn over time. I mean, both could be kind of true, but only supported by the data. I would suggest here, total volume of freshwater withdrawn changed only slightly. Okay? Until... Well... Again, we're looking at 1980 to 2005. Okay. I didn't want to misread again. Water use is more efficient when the same volume of water is used to support a larger population. So clearly we've become more efficient since 1980. Look at the same graphs. Think about the trends of both the population and the volume of fresh water withdrawn. Same graphs. Between 1980 and 2005, the volume of fresh water withdrawn in the U.S. population both grew steadily. This means that the water use was efficient. In 2005, it was in 1980. After 1980, the volume of groundwater and other freshwater withdrawn leveled off, but the U.S. population continued to increase. This means that water use became more efficient. I like that. If we had the same efficiency, then we would have to keep withdrawing more and more water. So humans got better using it to support a larger population. Advancements in engineering. New ways of solving the same problem. Here we go. Here's depletion. Humans need to withdraw groundwater in order to use it. Groundwater comes from aquifers, formed underground over long periods of time, sometimes several thousand years. By drilling wells into the ground, humans can pump water out of these aquifers. Oops. The rate at which humans withdraw groundwater is much faster than the rate at which these aquifers recharge or refill. As a result, the groundwater supply is being depleted or reduced. So this is saying that, going a little more in detail to the water cycle that we've learned and studied, that infiltration takes a long period of time to replenish large bodies of groundwater, large aquifers. The total volume of groundwater that has been removed and not replaced is called groundwater depletion. As groundwater depletion increases, groundwater will become more difficult to find and more expensive to withdraw. Okay? Which statement correctly describes how human activity affects groundwater on Earth. Groundwater is difficult to extract from deep aquifers, so humans will not affect the groundwater supply until they develop new technologies to withdraw the water more easily. Or, because groundwater recharges more slowly than humans withdraw it, humans could use up much of the water stored in aquifers. We have the technology. We've had technologies for thousands of years to reach water underground. We have wells. But we can outpace. We can use more and deplete more water than is available in an aquifer. If our rate of depletion outpaces the rate of replenishing, then you turn water into a non-renewable resource, which we did discuss in the beginning. As people withdraw groundwater from aquifers, groundwater depletion increases. The bar graph shows the volume of groundwater withdrawn in the United States in a given year. The data shows the volume withdrawn in each year. So water withdrawn, it's the same graph as before. Now depletion. Depletion has steadily increased. Almost a linear increase. Use the data to complete the statement. The volume of groundwater depleted by 1980 was blank the volume in 1980 withdrawn. So groundwater depleted by 1980 about almost 600 cubic kilometers, and then withdrawn it was about 110 cubic kilometers. So we depleted almost 6 times more than was withdrawn. Look at the same graphs, which show the volume of groundwater. Yep. Think about each volume change between 1950 and 2005. The volume of groundwater withdrawn in 2005 was about 9 times as large as the volume of groundwater withdrawn in 1950. 2005, 9 times as greater. 110 and 45. 110, 45, that's about double. Not so much 9 times. Okay? How about depleted? 2005, 1950. Depleted, you get about a little over 900 cubic kilometers and a little over 100. 100, 900. Yeah, that's 9 times as large. Then they kind of show you that, if you pump water out, you create a void, you create empty space. And we know that you can't really have empty space in and around the earth, so gravity will take over. If there's nothing supporting land above it, the land will collapse. And like we have here, a sinkhole. So geological impact, just from pumping water out of the ground, especially in large aquifers. Look at the same graph, think about how withdrawing groundwater affects groundwater depletion. The volume of groundwater withdrawn per year did not continue to increase after 1980. The volume of groundwater withdrawn per year did not continue to increase. No, it's mostly stayed relatively the same. But total groundwater depletion continued to increase because groundwater was still being withdrawn. Yes, depletion did continue to increase. Okay? Because the volume of groundwater withdrawn per year did not continue to increase after 1980, groundwater was not depleted any further after 1980. Now, this definitely suggests that there was an increase in depletion. Less in those 5 years of 1980 and 1985, but definitely still an increase in depletion. So depletion is always going to continue to happen because you're continuing to withdraw more. Even if it's the same amount of water, you're still depleting it year by year because you're still withdrawing it year over year. All right. So it's 1980. Since 1950, groundwater has been severely depleted in many U.S. regions. In recent years, farmers and engineers have come together to find solutions to conserve fresh water, including groundwater. For example, farmers are making an effort to provide a precise amount of water to their crops. Older irrigation systems use much more water than crops needed, but engineers have developed newer irrigation systems that use water more efficiently. These irrigation systems provide the right amount of water directly to the roots of crops. As a result, farmers can use less water and still grow healthy crops. That's kind of what I want to talk about once we get through this, is could you have self-watering soil? So again, more efficient use of soil and water irrigation. Which of the following statements explain why it's necessary to find solutions to conserve groundwater? Multiple sources of liquid fresh water on this earth, including groundwater? To conserve groundwater? Groundwater is a limited resource, is being used up quickly. That's definitely a reason why we have to conserve it. When groundwater is withdrawn from aquifers, it cannot easily be replaced. That's also true. Groundwater use has become more efficient, but groundwater depletion has increased. That is also true. We're not really focusing on fresh water on the surface. Ooh, extra points. I'm not going to get into extra points. But that was the IXL from last Monday, looking at groundwater, how it can be a non-renewable resource, because humans, especially in the United States, are depleting groundwater faster than it can replenish by the water cycle naturally. These aquifers are running out of water. So, something to keep in mind. Self-watering soil from University of Texas. Soil that waters itself. So down in Austin, these engineers have developed an idea where you could store water in the soil, so you increase the soil moisture, and then that water can be released over a longer period of time. Engineers at the University of Texas at Austin can pull water from the air and distribute to plants, potentially expanding the map of farmable land around the globe to previously inhospitable places and reduce water use in agriculture at a time of growing droughts. Team's atmospheric water irrigation system uses super moisture absorbent gels to capture water from the air. When the soil is heated to a certain temperature, the gels release the water, making it available to plants. When the soil distributes water, some of it goes back into the air, increasing humidity and making it easy to continue the harvesting cycle. So you're kind of slowing down water loss in the soil, and you're kind of having plants in the soil ration the water that's available to it. Okay, so kind of cool that these gels capture water from the air and then they retain it in the soil. So works in very arid or very dry places. You know, southern United States, southwest United States. That's a big deal right now. Each gram of soil can extract approximately 3 to 4 grams of water. Depending on the crops, approximately 0.1 to 1 kilogram of the soil can provide enough water to irrigate about a square meter of farmland. It's not amazingly efficient, but it is efficient. The gels in the soil pull water out of the air during cooler, more humid periods at night. Solar heat during the day activates the gels to release their contents into the soil. So you are storing water during the night for the day. Solar radiation during the day breaks down the gels and releases the water. A lot of desert plants, though, do photosynthesis or store water during the nighttime. So I wonder if this is dependent on certain CAM-type photosynthesis plants. They ran experiments on the roof of the Cockrell School's Engineering Teaching Center building at University of Texas in Austin. To test the soil, they found that the hydrogel soil was able to retain water better than sandy soils found in dry areas, and needed far less water to grow plants. During a 4-week experiment, the team found that soil retained approximately 40% of the water quantity it started with. In contrast, sandy soil had only 20% of its water left after just 1 week. 20% increase. That's pretty good. In another experiment, the team planted radishes in both types of soil. The radishes in the hydrogel soil all survived a 14-day period without any irrigation beyond an initial round to make sure the plants took hold. Radishes in the sandy soil were irrigated several times during the first 4 days of the experiment, but none of the radishes in the sandy soil survived more than 2 days after the initial irrigation period. So even with regular irrigation during the first 4 days, none of the radishes survived in sandy soil, but in UT's hydrogel soil, they all made it 14 days with just some initial watering in the beginning. That is very efficient and very, very good use of resources. So again, engineers need to be more efficient with the water that we use. You want to sustain a population? Well, you need food, but you also need water. So you got to use the water sparingly where you can when you're trying to farm, since it's probably our biggest use of water. Other applications, it could potentially be used for cooling solar panels and data centers. It could expand access to drinking water, either through individual systems for households or larger systems for big groups such as workers or soldiers, so out in the field. Very cool idea. I kind of want to know what the hydrogel's made out of. It's got to be something that has almost a very low melting point. It's got to be something that has a melting point or a freezing point, solid to a liquid, that is within day-night. And it can't be too close together. Interesting. I also gotta say, like, what time of year did they do this in? What time of the year did they do this experiment in growing the plants? Was it in the springtime? So, what's the climate like in Austin, Texas in the spring? 60s, 70s? 12 hours, 13 hours, 14 hours of sunlight as you go into the almost summertime. So it's got to have like a melting point around 70 degrees Fahrenheit. And you also need it to freeze. You need to turn back into a solid. Because they also don't really say, does the gel refreeze after it essentially melts? Because it's got to be a solid, retain water, melt, refreeze itself, and collect water again. Or does it become a solid when it has water? So that's a chemical reaction. So I just want to know if it's a physical change or more a chemical change based on how this gel works. Of course, they're not really going to say what it is because they probably want to patent it and then sell it. But if you want to read more about it, it's linked in the description. Hope you guys have a good rest of your Monday. See you tomorrow. Keep an eye on that email for any announcements for in-person or distance learning this week. See you later.